Okay, so good evening, good morning to everyone. Welcome to this new webinar. And as you know, we are going to talk about the new material model we implemented in OpenSees, which is the ASDConcrete3D model. So let me just share my screen. Okay, and I move on this other computer. Okay. Okay, so before we start, you know that we just released this week version 2.1. The new version of this material model has been implemented in version 3.0. Then we made a couple of improvements. Guido, can you take care of muting and all this stuff? Thank you. So version 3.2.1 is the latest version of the material model. And this model is now inside the official OpenSees repository. But as you know, it takes a little bit of time for the OpenSees maintainers to compile the new version. So if you want to test it right now, as usual, you can compile the version found here in the Professor Tarke's website. You can go here and download the link. You can find all the instructions to reach this website from our web page. Okay. But anyway, it is on the OpenSees repository now. So here I have a brief presentation about the points that we are going to talk about. So here are the contents. So I will start by a brief description of the ASDConcrete3D, where you can find the documentation, the references. Okay, so I will just talk a little bit about the theory very briefly, but then you have the documentation to go more in details. Then I will spend some minutes about material testing, so that I will explain you what is the meaning of each and every parameter. And you will see that it's much easier to use than the damaged PC 3D model because it has less parameters. Let's say it's more optimized. After that, we will do a numerical application, which is basically the same model we did in the previous webinar on reinforced concrete shear walls, which is the shear wall by Mastianek. I will be testing the same wall with different mesh resolutions, so you will understand what is the behavior with a fine mesh, with a coarse mesh, and so on. What's the effect of including or not the IMPL-EX integration scheme? Then a new feature that we implemented in SDKO. I already talked about the IMPL-EX algorithm in previous webinars. You already know that this kind of algorithm, due to the explicit part of the integration, it introduces some errors that can be reduced by keeping a time step quite small. But now we have an automatic error control, okay? So it's easier for users that are not aware of how the IMPL-EX works. So it will be much easier to keep the error under control. And then I will show you a new feature that we have in version 3.2.1, which is the crack plot, okay? Which is very convenient for visualizing the crack pattern, especially when you have very coarse meshes, okay? So a little bit about the theory. You can find the theory of this material, of course, not in the old OpenSees documentation, because in the old OpenSees documentation, it is not maintained anymore. The new OpenSees documentation is on GitHub, okay? So here is the link to the material model, but if you want to find the latest OpenSees documentation, you can simply go on Google and search for OpenSees GitHub documentation. This will lead you to the OpenSees documentation repository. Well, here is where the source code of the documentation is taken, but here you have a link to the compiled documentation, okay? And this is where all the new elements of the new material models will go from now on. So it is a material model, so we go under command manual, material, and the material, because it is a three-dimensional model. And here you can find ASDConcrete3D. Okay. So here you have a brief description. Then as usual, you have the full OpenSees command, and you will see that in the SDKO user interface is actually much easier. Here you have all the parameters, but basically it's very easy. You have the typical tag of the material model, the elasticity constants, so Young modulus and Poisson ratio, and then a bunch of optional parameters, which is the mass density. Then these lists here are lists for defining the tensile and compressive behavior. But this time, instead of using a closed form equation, as we did in the DamageTC3D, now you can input the tensile and compressive behavior by points. So you have the maximum freedom about defining the tensile and compressive behavior of the material. Then you have some parameters for the implex algorithm, okay? And some new features that I will be talking later on, which are the crack planes, okay? So when I will talk about the material parameter, I will talk about how you can set up the tension and compression hardening laws, how you can switch on the implex algorithm, and then the crack planes, which is basically something that we introduced in this model, which is a sort of anisotropy of internal variables. And then I will talk a little bit about the rate-dependent model, okay? So here you can find the meaning of each parameter, and I will explain them now using some examples. Then you have the theory. Okay, if you are interested, you can go here and you can understand how the computations are done. This is a schematic representation of what a plastic damage model is. Okay, so basically, let's assume you are here at this point, you do an elastic prediction, then you do a plastic correction, and then a damage correction. And basically, at this point, a plastic damage model combines the effect of plasticity, so you have inelastic deformations, but you also have stiffness reduction due to the damage model. Always in this documentation, you can find some notes about how to use it, what are the responses, and then you have a bunch of examples, but plain OpenSees examples, okay? And now I will talk about instead how to use it in SDKO. Here, for example, you have a Python file to use OpenSees Py to automatically draw the damage surface in the plane stress space, and then how to set up tensile and compressive behavior. And then you have a few references, okay? Well, the first reference is one of our papers about this constitutive model. And here instead, you have the main reference about the implex algorithm, okay? Okay, so we can move on. And let's go back here. So first I will talk about testing the material parameters, okay? So let's open, oh, and then I want to show you all the materials that you will have by tomorrow on the website. So here is the folder about today's webinar. You will find the PowerPoint presentation. Then a first folder, which is called material test, where basically you have a simple file with 3 material models. We will just do material testing here. And then an Excel file used to calibrate some of them. I will show you. And then after this, you will find 5 folders. All of them are about the messianic shear wall, okay? And basically, some of them are using a very coarse mesh, some of them are using a coarse mesh, then a fine mesh, because I will explain you what's the difference using different mesh sizes. And some of them are using the standard implex algorithm, the standard implicit algorithm. Some of them are using the implex algorithm, okay? So let's start by testing the material model. So I go here and I open the file that you can find in the first folder, material test. As you can see, there is no geometry. I simply created 3 materials to explain you how it looks like, how you can set it up. Okay, so this is Excel. I need it later on. So when you create a new ASD model, this is what you will see, okay? Let me make it a little bit smaller. Okay. So the first thing that you have here under the mass group is basically the optional mass density, okay? We will not use it today because we're going to do static tests. Then you have the elasticity parameters, so Young modulus and Poisson ratio. Then here, this is the session where you define the tensile and compressive behavior. In OpenSees, you have seen that you can basically, you have to input all these lists, okay? Strain, stress, and damage, and strain, stress, and damage for tension and compression by points, okay? Now, since it can be annoying repeating the same equation each and every time, we created some presets. So basically, you can choose from a user-defined approach, where basically you can define the tensile and compressive behavior by points, or you can have some built-in presets, which are very easy to use. For example, if I use the preset concrete 1P, where 1P stands for one parameter, basically this is a preset that requires just one parameter, which is the compressive strength of concrete. And then you just need to tell me what is the unit system you are using. Then I will explain you why. But basically, given the compressive strength, we compute all the other parameters according to model code 2010. So for example, the tensile strength will be 1/10 of this one. The peak strain at compression will be this one divided by Young modulus times 2. Okay, so the typical 0.002, when this one is proportional to this by a factor of 1000. And then the fracture energies are computed as well using the model code. For example, in this case, we compute the fracture energy as like GT equal to 0.073 times the FC to the power of 0.18. Now, why do I need the unit system we are using? Well, because this equation is calibrated, it works if FC is given in megapascal, okay? So if you are not working in megapascal, you simply have to tell me what is the unit system you are using, and I will do the proper change of units, okay? So this is the reason why we require the unit system. And then GC is simply computed as 250 times GT, okay? This is the equation that we always used in the damage TC3D model, but in this case, they are automatically computed. Okay, so basically, this is the first kind of preset. Very fast, you simply input the compressive strength. If you want a little bit more freedom, like for example, you are fine, and let me show you how it looks like. For example, let me go in a monotonic test, and I want to push it like this, 0.01 as a strain. Oh, and this is something new you have found in version 3.2.0, the characteristic length in the material tester. Now, if you remember, in previous version of SDKO, there was not this input, okay? So basically, I was doing a test on a unit triangle. It means, for example, if I'm using millimeters as length, I'm testing a material test of a 1 millimeters times 1 millimeter, okay? So if you do a test like this, you will see that the fracture energy is very high. This makes sense because it's like I'm doing a test on a 1 millimeter long specimen. If you want to see what is the behavior, so the stress strain displacement curve of a certain size, you can put it here, okay? This is not going to change the behavior of the material model. It's just a preview for you to understand how the material will behave with a certain mesh size. Like for example, if I want to use a mesh size of 300 millimeters, the G that is here, which is basically the equation that I showed you before, will be regularized using this characteristic length. And this is actually how it will look like inside a material, inside a finite element which has this dimension, okay? So the shape of the tensile curve is taken from model code. So basically, as I told you, in the one parameter, the tensile strength is 1/10 of this one, so 3 megapascal. And then the model code suggests a shape of the tensile curve like this. So you have a first point here, which is at 0.9, the FT, okay? And up to here, the behavior is linear. Then you have a linear hardening up to a certain value, which was, I think, 1.5, this one. Then you have a bilinear softening, and then a residual plateau, which is almost zero. It's not zero, but it's a very small tolerance. Okay. Now, the fracture energy is divided in such a way the first part of this triangle takes 1/5 of the total fracture energy, and then you have the remaining part on the other side. Okay. So this is the shape in tension, and let's see in compression. I will push it to, I don't know, 0.01, 10 times more. And in compression, you have a behavior like this. So a standard Ken-Scott-Park model. So it will be very compatible with other material models in OpenSees. So you have a first parabolic hardening up to the peak strain. And the peak strain in this preset is computed as FCP divided by the Young modulus times 2. Okay. Then you have a linear softening and a residual plateau, and the residual plateau is computed as 1/10 this value. So it is 3 in this case. Okay. So this is the monotonic behavior. Now, this kind of models, this kind of parameters are taken from model code, and they work well for unconfined concrete, standard concrete. So if you're working with standard concrete and you are fine with the shape of the presets that we implemented, you can use this one. Sometimes you may want to have more control over the fracture energy, for example. So let's say you are fine with the shape that I'm using for tensile and compressive curve, but you want to adjust the fracture energies. Well, you can move to the concrete 4 parameters. Okay. When you move to the 4 parameters, you are required to give FCP, then FT. Okay, so in this case, it can be different from 1/10, but in this case, I will take the same. Let's say for GT, I want to do the same thing, 0.14 more or less will be that equation. And then I want to use a very high fracture energy to simulate a compressive, a confined concrete. So instead of being 35 as the previous equation, I can put 66, for example. And as you can see, I will increase the fracture energy in compression. Okay. Now, and this is the 4 parameters, and you can see it here. I already saved it here. Okay, 4 parameters. Otherwise, if instead you want to simulate some other kind of concrete, for example, someone on our forum requested, they wanted to model basically IMPL-EX concrete, and there was a problem because this kind of concrete has a behavior which is not like plain concrete, where basically you reach a peak and then you go in softening. Instead, you have a sort of plateau, small hardening, and then you have a quite good ductility, and then there is softening. Now, this was not possible with the damage TC3D. Okay. Now, something like this can be done very easily with the new material model. Okay. Now, we don't have a preset for that, but when you don't have a preset, you can go under user defined, and then you define by points the strain, the stress, and the damage variable for both the tensile and compressive curve. Okay. So I will show you very briefly how you can do that. But here, for example, I set up already something. So let's say that the first part of my tensile behavior is like the one of the model code. Okay. So my peak will be FT. Then this one will be 0.9 FT. Okay. So let's place this point here. So this one will be the strain at this one. So it will be the behavior up to here is elastic. So 2.7 divided by the Young modulus. And this one will be twice this value. Okay. So if I input these values here in my TE, well, I already did it. Okay. So you can put the values of strain. Then you can put the values of stresses. So I said 0, which is the first point, then 2.7, which is 0.9 FT. Then I have FT. Then I have a small hardening, which is basically this point here. And then I go down to a residual plateau, which in my case, 0.5. And then I want to keep it constant. So I put another 0.5 here at a larger strain. Okay. So if I test it now, under monotonic test in tension, let's see, up to 0.02, 1000 steps. Okay. I have. Okay, so I have a first point here. Or let's bring it a little bit less so you will see the first part. Okay, so up to here was like the standard plain concrete. Then I have a small hardening up to, let me see, 0.0015. Okay, so if I move it to 2, you will see some softening starting, and then it will start, it will go up to a certain point. Okay, let me push it up to 0.01. Okay, so this is the behavior you have in tension. Then in compression, I did something similar, but without the strain hardening, without the parabolic hardening. I did a simple linear hardening here. So if I test it in compression, you will see something like this. So 25, which is here, linear elastic up to this. Then you have the peak point at peak strain. If you want, you can insert more points and you can simulate a parabolic hardening here. Then a linear softening and the residual plateau. Okay. Now the point is, how do you set up the damage variables? Okay. Let me do a quick test, putting everywhere 1. So you will see what they mean. Okay, let's start by putting 1 everywhere. If I put a damage of 1 everywhere and I do let's go in tension, metric linear increasing, and I do 10 cycles, 100 each. Okay, well, I'm in compression now, but let me do it in time. Okay, you will see something like this. Okay, so it will go damage. So basically, you will not have any plastic deformation. Every time you unload it through the center. Okay. On the opposite, if I put 0 everywhere, you don't have any damage at all. So the model will be just plasticity. Okay, so it will go here and it will unload with the same elastic stiffness. Or you can put something in between. Okay. Now I decided to calibrate it, defining the plastic strain that I want on each point, and then I can compute the damage variable. Or you can give the damage variable. It's up to you. Okay. Now you have to play with it a little bit to understand how it works, but it's easy. Okay, so if I put these ones, okay, you will see a behavior like this. So it starts with a certain plasticity and then it reduces up to a certain point where basically plasticity is not available anymore. Okay. Fraction, I copy these values here. And I do the same thing here. And then I can do a full test like cyclic symmetric linear increasing, 0.01, 100 subdivision, 10 cycles. Okay, so this is the behavior that I will obtain. Okay, so you can play with it. Now, one thing that you can notice right now is that when you switch from one of the presets to the user defined, you will find this one that will appear. Okay, so when I go in one parameter, there is no topic about regularization. Why? Because in those presets, we automatically switch on the automatic regularization because we are deciding the amount of fracture energy. Okay. Instead, when you specify the tensile and compressive behavior by points, it's up to you. Okay, so you know if you want to regularize it or not. And if you want to regularize it, okay, you simply switch on this box here. And since they are stress strain points, you have to tell me what is the reference length of the specimen from which you obtain this material data. Okay, why? Because, for example, if you obtain this stress strain point from a specimen which was 300 millimeters and you obtain a mesh which is 300 millimeters, there will be no change. Okay, but imagine that I have a mesh which is smaller by 1/2 of that one, like 150. My material model will increase the fracture energy by a factor of 2. Okay, just to keep the same amount of ductility. So you will see that the amount of fracture energy changes. Why? Well, the equation is simple. So since you are giving me these points as stress strain point, like you are giving me a curve like this, where basically this is sigma and this is epsilon. If you obtain experimentally this curve, it means that you had a specimen, okay, which developed a crack, but what you measured was a displacement jump, okay, and then you divided the displacement jump by a certain length, okay. This is this reference length. So in the experiment, they obtained a displacement jump, they divided by a length, and they gave you a deformation. Now, the area that you have here is a specific fracture energy, specific to the size of the specimen. So what I'm doing inside, basically, is taking this G, multiplying it by the reference characteristic length. So in this way, I will obtain the real G, which is equal to small g times LCH ref. And then I divide this one. So I obtain the specific fracture energy for my element, which is the real G divided by the length of my element, okay? Now, of course, if the length of your element is equal to this length here, you don't have any change, okay? I've been talking about this one every time, so this is the typical problem of fracture energy regularization. Clear drawings. So just to tell you, if you use one of the presets, you don't have to worry about it. If you use user-defined stress-strain curves, you have to give me the size of the specimen from which you obtain this data, okay? And I will perform automatic regularization. Then you have a few other stuff. Let me explain it to you with the standard 1D parameter. Well, you have the integration scheme. It can be implicit or implex. You already know the differences between them, and I will show you some example later on. There is not so much to say about this at this point. One new feature instead is the concept of crack planes. Now, this model is an isotropic model. It means that it behaves in the same way in all the directions, so it does not take into account the directionality, which is fine for concrete because it is an isotropic material, but it is isotropic only at the beginning, okay? So when you start having crack, it actually behaves anisotropic. Now, what we did is a simplification. So the model is still isotropic, but the internal variable have memory of the different directions of the crack, okay? So now by default, this is a standard isotropic model. If you switch it on, you activate, and which is here, activate an isotropy of internal variables on multiple crack planes. Now, what you have to input here is the number of crack plane for the tensile behavior, for the compressive behavior, and the smoothing angle. Now, I didn't have time to put the documentation of this one in OpenSees, but I will do it in the next days. But just to explain it to you, what it means is that, let's imagine that a material point is a sphere, okay? So in 3 dimensions. Now we'll take only in 2 dimensions just to show you better. Okay, imagine in 2 dimensions, I have a sphere like this. Now I consider only 90 degrees here, because then I will duplicate everything. Then this number is telling me in how many portions I want to divide this sector of 90 degrees, okay? So in this case, I'm dividing in 4 portions. So basically, I'm going to have some normal vectors in all these directions, and each one of them will store internal variables. So basically, if I'm loading a material point in one direction, here I will develop a certain damage up to this point, for example. But in the other points, I don't have any damage, in such a way that if I will load later on in another direction, I will not start with the same level of damage, but I will start with the level of damage that I have here, okay? So this is basically used to activate a sort of anisotropy of the damage. This one is a smoothing angle. Why? Well, because it makes sense that if I have damage in this point, in the neighboring, the same damage will be, this damage actually will affect a little bit also what's going on in the neighboring normal vectors, okay? So basically the smoothing angle here is given as 45 degrees. It means that if I flatten this one, like here I have the angles, but if I flatten it on an XY plot, and here I have the damage, for example, and here I have the angle, and this vector, this point here is at an angle of 0, which means this point, and I reach a damage of 1, the other points, in the other vectors, I will not get 0, but I will smooth them using a Bell function, okay? So this is basically used to smooth the damage in the immediate neighboring of a crack. I will do much more documentation about this. It will be much clearer, but for now, let's just say that if you want to activate anisotropy, you can simply switch this on and you can leave these default values. They are pretty fine. And I will show you now what happens with them. So let's switch it off for a while. And let's try to do a cyclic shear test. Okay, so I move to shear. So I will go here and I want to do a cyclic shear with a certain level of precompression, like -2 megapascal of precompression. And I want to do a cyclic symmetric linear increasing. Not that much. I want to do something like this. 10 cycles, 100 divisions each cycle. Okay, let me push it a little bit more. Okay, so basically this is the behavior that I have now. Probably even more points, so it will be easier to visualize. Okay, so this is what I have now with without the crack planes, which is basically also what was happening before with the damage DC3D model. Now, if you can see here, I'm loading on the positive direction, and I'm reaching a value, a certain value here, which is the tensile strength plus the effect of the precompression. So I start here at around 4. Then I go in strain hardening up to 4.5. I go down here, reach the same value. Then I have some softening due to the softening in tension and so also in shear. Now I have this softening and then I reach a peak residual value of 2.5. Well, when I'm unloading and loading in the other direction, I will find the same level of damage, basically. So I will start with the same level of damage. Graphically, it means that if I have a specimen like this, and I'm loading in this direction and I develop a diagonal crack here that was giving the first softening. When I load in the other direction, I don't have any crack, but I will find the same damage. So what I would expect instead is to load on the other direction and go back to the initial strength and then develop another crack in this direction here, okay? And then basically you can activate this by simply, and let me show you this one on Excel. So I extract the data, I copy the strain, the gamma 1, 2 and sigma 1, 2, and I will try to put them here. And let's do a graph so we can superimpose this to the other one. Okay, so this is without the anisotropy of the internal variables. Then I go back here, I activate them. I don't want to change any settings. These one are fine. I run the test again. Now you can already see a difference. Okay, so I go up to 4.5 here, strain hardening. I go down here, reach the same value, strain hardening. Then I have softening up to 2.5. But when I load here, I reach the same point. So I have to put softening also in the other direction. I have to open a crack in the other direction. Then I go in softening and then I reach the previous value. Okay. So if I compare this one with the previous, you will soon see what's the difference. So select data, add, and I want to add this one. Okay, so it's pretty evident now what's going on. The first part is the same. The second one is similar, but it's not affected by the previous strain hardening. Then you reach softening, but here you reach the same value you had before. The meaning is that in that new direction, I still have to develop a crack to have this softening. Okay, so let's say this is a more realistic approach for analyzing the cyclic behavior. Because if you remember, those of you who already tested the damage DC3D under cyclic test, there was a problem in cyclic testing. Basically, the damage was accumulating too fast, and it was partially due to this aspect here. Okay, this is fine. And what else? Oh yeah, you have the last stuff here, which is the constitutive tensor type. Well, now you can choose between tangent and secant. I do recommend to always use the secant, because even if it takes a little bit more iterations, it will be much more stable. Okay, if you choose the tangent, and you're not using the implex algorithm, you may have negative eigenvalues and it can create some problems. So I recommend to just use the secant stiffness every time. But there is another feature, which is the rate dependent model, okay, which is based on the viscoplastic regularization. So if you want, you can use the eta parameter to activate the viscosity. What does it mean? So let's go back to a uniaxial test. You will see now what it means. So let me go back here and let me do a cyclic symmetric linear increasing minus 0.01 and 0.1. Okay, so without the eta, if I do a test like this, okay, so this is the behavior that I have. Okay, I can use also less points, it will be fast. Okay, now if you want, you can include rate dependency. Okay, so the viscosity of concrete, and for example, this is useful if you are doing dynamic analysis of with a fast loading rate and you want to have the effect of the concrete stiffening due to a higher loading rate, you can apply the viscosity parameter. Now, just to tell you what's going on, if you put the viscosity parameter, which is less than the typical time step, which now is a total duration of 1 second divided by 1000 steps, which is 100 per 10 cycles. So if I put a value which is significantly smaller, like instead of 1 to the minus 3, I put 1 to the minus 5, you will not see anything here. But if I start increasing this one, it will be more evident. Like, for example, let me put it equal to the time step. You will now see that the stress basically can exit the yield surface and then go back. Now I want to exaggerate it just to show you the effect of the rate dependency. Okay, so basically you are allowed to exit the yield surface and then the stress will relax back to the standard model. Okay, this will not be used very often, but if you're doing dynamic analysis with very fast loading and you want to consider rate dependency, you can use this one. Okay, so this is all about the material parameters. And now I will show you how I did the same model that we did last time. So the Mastianic shear wall with the new material model. So let me close this one. You will find all the models here. So Mastianic shear wall coarse. I will start with the very coarse one, okay, in implicit. Then I will do the same with the implex, and I will show you the differences also in terms of time. Then I will do a coarse mesh, once again, implicit and implex. And then I will show you finally what happens with a very fine mesh. Now, for reasons of time, I just use the implex algorithm for the very fine mesh. Now, all of them are set up for the standard sequential OpenSees. Just the fine one is using OpenSees MP. Okay, once again, for just speeding up the analysis. So I will start by opening the shear wall very coarse. Oh, and the geometry and the settings are the same everywhere. Okay, so I will explain them only once. Okay, so if you open this one, the geometry is very simple. Actually, I decided to keep it very, very simple. So you have a single shell here as a geometry. It has 3 cuts. Okay, basically the 3 cuts are used for creating the 2 vertical columns. Okay, now if you don't remember the details of this specimen, you can watch our previous webinar, and there are also the references there. Okay, but basically it is a shear wall, 100 millimeter thick, and then you have 200 times 200 millimeter boundary columns. And that's why you have these 2 cuts here. Then I put another cut in the middle just because I need a point in the center to apply the imposed displacement, but also to monitor the displacement controlled analysis. Okay, so this is the reason why I put a cut in the middle. So if I go in physical property, you will see that you have different properties for the 2 faces. These 2 faces here, which is the inside wall. Then you have the boundary columns in green. And then you have the top beam, which is an elastic beam. For the top beam, I simply used the edge on top of the shell. Okay, so it's a simple geometry. I have a linear time series for the application of the vertical loads. And then I have a cyclic time series, because in the previous webinar, we only did some monotonic analysis. Now I'm doing a cyclic analysis. Here I have the list of total displacement that I got from the paper. Okay. And the total duration will be 1 second. I will be using this to impose a displacement on top. So we'll do a load control analysis, but with an imposed displacement. Okay, so coming to the material properties, you have steel models using Menegotto Pinto. Already talked about these models. This is for the 6 diameter rebars on the web, and this is the 12 millimeter rebars for the boundary columns. Okay, so these are uniaxial materials. Then I have 2 instances of ASDConcrete3D. So the first one is the concrete for the wall. Okay, here I decided to do it very fast, so without tweaking too much the parameters. I simply put the Young modulus that I have from the paper, the Poisson ratio, and then I use the preset with the 1 parameter. I was curious to see if the presets were working fine for standard concrete. So I put the value, oh, here I'm using meters and kilonewton. Okay, so that's why you have this value. It was 25.5 megapascal, basically. I activated the crack plane because I'm doing a cyclic analysis, so I want them. I'm not using any viscosity, it's a static analysis, so I don't need it. I will start with the implicit integration, okay? And the second tensor. So this is very easy to set up. And this is the behavior that I have if I use a mesh of, let's say, 0.3 meters, okay? So pretty similar to the other one. Now for the confined concrete. Why the confined concrete? Well, because this is a shell model. So a shell model is not able to automatically compute the confinement because I'm not modeling the stirrups and I'm not modeling the 3-dimensional model. Okay, so basically it is always in a plane stress condition, so I cannot fully compute automatically the confinement. So if you want, you can pre-compute the confinement. But if you want to do so, you need to create another material model. As I told you before, instead of 1 parameter, you choose 4 parameters, and then you choose a slightly higher peak strength, then the tensile strength, and then, as I told you here, I just doubled the amount of fracture energy, okay, with respect to the other one. Okay, so this one will have a much larger fracture energy in compression. Once again, implicit integration scheme, and I activated the crack planes because I need them for cyclic analysis. From here on, everything is equal to the previous webinar. So basically, I have uniaxial material. They are being converted into rebar materials with a certain angle. So this is basically a wrapper that converts a uniaxial material into a set of, in a plane stress material, which is a smeared representation of rebars. So basically for the web, I need 6 diameter rebars with an angle of 0 degrees, 90 degrees. And for the column instead, I just need the vertical, the longitudinal rebars, 90 degrees, okay? If you remember, the degrees here are relative to the local system of the shell. So my local system has an x-axis, which is this one. So 0 means rebar oriented in this direction. 90 degrees means rebars oriented in this direction. Okay, so that's why in the middle I need 2 of them, x and y, and on the boundary columns I need only 90 degrees. Okay. Okay, perfect. And then once I have all this material, I just have to put them into shell layers. Okay, so I have concrete, and 3 layers of rebars and the relative thicknesses. If you remember, the thickness of the concrete is the real thickness. Okay, so it should sum to 0.1 meters, while the thicknesses of the rebars instead are just equivalent thicknesses. Okay, so basically is the area of the rebar divided by the spacing. And here I just put, in the name I put the spacing here. It was 6 diameter rebars with a spacing of 180 millimeters. Okay, so well, the top beam is simply elastic. Okay, so it's a 0.4 times 0.4 rectangular concrete. concrete beam, and I just put elastic material. It's just used to as a, let's say, a rigid beam to apply the load. So finite elements, I'm using the ASD shell Q4 for the shell parts, so the web and the boundary columns, and a simple elastic beam column for the top beam. Okay. Now boundary conditions, I have a fix at the base. Okay. Here I'm fixing only the X, Y, and rotation about the axis. Then I will fix everywhere the out of plane displacements. Okay, so displacement in the Z direction and the 2 out of plane rotations. Then I have the self weights for the web, self weight for the boundary column. Why says that? Because it does double the thickness. The self weight of the beam, which is as an edge load, because it is imposed on the top of the shell. And then the push load, which is actually an imposed displacement at this point. It is sufficient because actually the actual stiffness here is very large due to the elastic beam. Okay. Now the imposed displacement should be 1 because actually I put the real displacement values here. So if you see these values, they reach the real values of 3.5 centimeters. Okay. So you can either put the real values here and here you put a unit value, or you can normalize the cyclic load path and put the real value here. It's the same, okay? You just have to be consistent. So at the end of the day, the value of the time series times the reference value should give you the displacement that you want at the end, okay? So once you have this, you have a recorder, boundary condition, gravity loads, gravity analysis, then you apply the push load. Then I created a monitor and a displacement control analysis, which is actually a load control analysis because I imposed that displacement. Okay, I'm using 10,000 time steps because this is actually a dynamic cyclic analysis, so I need to use a lot of time steps now. Okay. Well, what else? I'm just using transformation method, all the setup for static analysis. Okay, nothing special here. Duration should be 1 because it should match the total duration of the time series. Okay. Now all the settings are equal for all the other models. Okay, so I will not repeat them again. Now, if you run this model, you will obtain these results. So let me go in very coarse implex. So if I launch the monitor, and I don't want to waste time here, so I already ran the analysis. It took 4.5 minutes to run the entire analysis, okay? And as you can see, the results are much, much better than what they were before with the damaged TC3D model, okay? They are matching very well, but as you can see, they can represent this pinching effect, okay? Which is something you were not able to see with the damaged TC3D model. Now, the time is this one. 5 minutes for 10,000 time steps. And the mesh, as you can see here, is very coarse. So the interesting thing is that in this model, I'm using an extremely coarse mesh. And even if I'm using this extremely coarse mesh, the material is very good and it gives a very good prediction, okay? Even with a very, very coarse mesh, which is basically 4x4 elements, okay? Now, if I go in post-processing, and this is one of the things I wanted to show you about this new material model, which is the new feature, which is the crack plot. Okay. Now, if you remember, when you use a very coarse model, a very coarse mesh like this, and let me go in very coarse implicit. I switch off the beam. I don't want to visualize it. Okay, now if you remember before, when we wanted to visualize the crack in a shell, basically we used to visualize section deformation, then the principal max strain, okay, and then we try to do some animation here. I cannot reach this point in just a second because there is this tool here. I don't know how to remove the, here you can remove like this. Perfect. So one drawback of visualizing the results with a very coarse mesh and with a surface plot is that the colors are very messy. So you don't really understand what's going on here, okay? So you can see that there is some sort of diagonal cracks here, but they're not so evident. It becomes more evident when you will have a very fine mesh. So we decided to create the crack plot. Okay, then I will explain you what it is. But basically, this material model now has two extra results, which is called crack pattern or crash pattern. Basically, crack pattern is for visualizing the cracks for the tensile behavior, so the opening cracks, and the crash pattern for the compressive behavior. Now, since this model has many cracks, we can actually store them, visualize them. Okay. Now we have a limit here. We are visualizing just the three most open cracks. Okay, so if you put yourself in the plane of the model, you will be able to see them, and their thickness will be proportional to the opening of the crack. Okay, and the value will be the crack width. So the maximum principal strain times the characteristic length of the element. Okay, so in this case, I'm having a maximum crack width of 1 centimeter. Now, if we watch the animation from the beginning, it will be much easier to understand what's going on in the model. Okay, so you can see at the beginning the opening of bending cracks here in the middle, then a first.
¿Es lo mismo de qué?
Sorry. Okay, Guido, can you mute the participant? Thank you. Okay, and so as I proceed, I will see more diagonal cracks developing at the center of the element. Okay. Now, even with a very coarse mesh, I'm still able to visualize what's going on here. Now, let's just move from this one, which is the very coarse, to the very coarse with the implex. Okay, so if you open the other one, if you go in wall very coarse implex, you will see that basically the model is exactly the same mesh, same properties. The only thing that I changed is moving from implicit to implex. That's it. I didn't change anything else. Material settings are the same, or probably I just increased. No, I use the same time steps. Okay. And now let's see the results. So before we had, just for comparison, we had 4.5 minutes, and this is the output that I get for the implicit one, this one. And now if I go in very coarse implex, this is the kind of output you can get. So the response is very similar. You will see here some instabilities. I will talk about them later, but it took just 1.4 minutes, 1 minute and 40 seconds. Now the reason for this instability is pretty clear, and I will explain them to you, but everything else is the same, basically. It took much less time. Why do you have some instabilities here? Well, what I did was to use an extremely large mesh size, which is 0.6 meters. It's very huge as a mesh. And the problem with this kind of mesh, and this is something you have to keep in mind, is that let's do a test in tension. Test in tension 0.001, and let's do a test with 0.6, and let me put some more subdivisions. You will see that if I'm testing a specimen of 60 centimeters, the behavior will be very brittle. Why? Well, because the fracture energy will be always that value. Okay, you just imagine that if I'm testing a specimen like this, and I have a crack here, or I test a specimen which is double the size of this one, but the crack will be the same thickness, because the thickness of the crack has a physical size. Here I store more elastic energy, so the total behavior will be more brittle, up to a point where basically I cannot increase the mesh size anymore, because actually this energy will be less than the elastic energy. So the only problem that you have when you use a very large mesh is that you may experience some instabilities due to the very sharp drop of the load displacement curve. Okay, so imagine if I use, for example, 0.8 or even 1 meter. With 1 meter, you will see a very sharp, load drop here. While instead, if I start reducing the mesh size, it will be more ductile, the behavior. Okay, so the only drawback that you have with a very coarse mesh is that you may encounter, especially with the IMPL-EX algorithm, some instabilities like this. Okay, but you will see that these instabilities will soon disappear as you refine the mesh a little bit. Okay, and then I will talk about also another settings for controlling the IMPL-EX algorithm. Now let's move to the coarse mesh. So this one was 0.6 meters, and we had already a good result. Now, if we move to the wall course with the implicit scheme, which is this one, and basically the mesh size was 0.4. So as you can see, if I use 0.4 here as a tester, you will see that the behavior, and let me do it monotonic, 0.001. You will see that the behavior now is not so brittle. So I think that I will reduce these instabilities. Everything else is the same. Here, I just changed the mesh size to 0.4. Now, let's see what happens. The wall coarse implicit. So before it was 4 minutes. Now it takes 60 minutes. Okay, I have very small instabilities here, but you can get rid of them just by reducing the tolerance. Okay. The behavior is very good again, and it does not depend on the mesh size, as you can see here. Okay, so pretty stable. But now we went from 4 minutes to 16 minutes just by reducing the mesh a little bit. Now let's see what we have instead with the IMPL-EX algorithm, because the IMPL-EX algorithm allows you to gain a lot of time when the mesh becomes very small. So if I go with shear wall coarse IMPL-EX, and I run this one. Okay, so this is the behavior that I get. Now I don't have that load drops anymore, because now the IMPL-EX error is localized into smaller elements, so I don't have those instabilities. You see the response is really stable as before, but it took only 3 minutes against 16 minutes. Okay, so this is very important to keep in mind. And the number of steps. Well, here I have precisely 10,000 steps. Here I have a little bit more because due to the non-convergence of the implicit scheme, I had to use adaptive time step. But pretty much we have about 10,000 steps for just 3 minutes. Okay. Now let's see the output of this one. Okay, so this one was the output for the coarse mesh. Is already visible with this kind of crack, but of course, if I refine the mesh, the output will be much nicer to see. So I go in coarse IMPL-EX, and I put the crack plot, and let's go to the beginning. Oh, the nice thing about the crack plot is that, well, by default it starts with the color map, but if you want, and it will be very nice for creating plots for papers. You can just switch off the faces. You can switch off if you want the mesh, and you can use a custom. You can create a custom color map with an all black color. How can you do that? Well, it's pretty easy. Let me show you from the beginning. You can go here, add a new custom map. You give it a color, a name, sorry, like all black. And you can just click on this point. Well, in this case, it's already black, so you leave it black. You click on the other point, sorry, double click. Then you change the color, and I want it black also here. Now, once you do this, it will be saved on your computer, okay? So you don't need to do it many times. And this will create this nice, I switch off also the beam extrusion. It will create this nice plot, okay? So it will be nice to superimpose to other plots, or just to create a plot for a paper to show the crack pattern, okay? So it's much better to visualize. Finally, you can find an extra example here, which is the wall fine IMPL-EX. In this case, I only use the implex algorithm just for reasons of time. So you will see the mesh is quite fine. But what you can get now is that basically this kind of mesh is already very good for this kind of analysis. But if you want to improve the solution, you can go with a finer mesh, which in this case it was 0.075 meters, so 7.5 centimeters. More or less, of course, which is constrained by the geometry. In this case, everything is similar to the previous test. The only thing that I did was to use parallel analysis, okay? So just to speed up the analysis, I used 6 partitions, and I just changed the analysis for parallel computing. So the parallel number and the mumps here, same thing in the displacement control. And then, of course, here I have to use OpenSees MP, okay? So if you run this analysis, you will see now a result which is much, much better, because already before it was fine. Like, let me bring this result here. So in terms of capacity, is fine. The only thing that you can see here is that the pinching here at this point is very narrow, okay, compared to the experimental result. It looks like in the experimental results you have a little bit more plasticity, but this is natural to see that in such a coarse mesh, because when you do the same with a fine, fine mesh here, you will see a much better result now. The times, of course, increased. It went from 3 minutes to 20 minutes, but you have a lot of elements. But now you have this nice, much nicer amount of plasticity here. Why is this happening? Well, this happens actually due to the rebars. Okay, I will try to explain you that. So let's go in post-processing. This is the coarse mesh, and remember that you have a crack of about 0.01 meters, so 1 centimeter crack here. Now, if I open, let me keep this one. I just want to open also the fine mesh. And I want to create another plot group with crack plot. And then I go to black. Well, here it is at the very end with some of the very close crack. But when I'm here, okay, so let me go to the beginning. Show faces, show mesh edges. Okay, as you can see, the mesh is much finer. Now the cracks are much more visible. And let's see what's going on. Okay, so you start here. Horizontal cracks, then this initiation of the diagonal cracks. The cracks here are much more smeared. Why? Well, because there is more reinforcement in the column, so it makes sense that you have a concentration of cracks here. And then you have the cracks on the other direction. Okay, so when you're up to here, you can see that the amount of cracks, except from this point now, because the wall is completely broken in those points, but typically here, the crack has the same size of the other model, okay? So 0.01, 1 centimeter more or less. Why? Because the crack opening is a physical quantity, okay? But the strain associated to this crack opening changes with the mesh. So imagine you have a crack, which is a 1 centimeter crack, okay? So you are trying to represent a crack like this, and this thickness is 1 centimeter, okay? Now here I'm dividing 1 centimeter for a mesh. Basically, I'm representing this crack with a smeared deformation over a mesh of 7.5 centimeter. Okay, so the strain here will be this value divided by 7.5. But on a mesh of 0.6 meters, which is 10 times this one, I will have a strain which is the same value divided by a length which is 10 times. So I will have a strain here which is 10 times smaller than the strain at this point, okay? This is just for equivalence, because the strain in strain softening does not have a real meaning. It's just the displacement jump divided by the length. Okay, so in reality, I would have a crack, but in the finite element approximation, I will have a smear deformation, like many, many cracks, such that the deformation here times the length of the element gives me this crack opening. What does it mean? It means that at each integration point of this element, I will have a smaller deformation, so the steel rebars will undergo a smaller plastic deformation. That's why with a very coarse mesh, you don't see that, you see a narrow pinching, okay? Now, just to explain you those points, let me create a plot, beam shelf fiber color map, but with the first database, so with the very coarse, and I want to visualize fiber strain. I want to visualize fiber strain on the vertical direction, okay? I want to plot the opening of the cracks here. So 2, and I want to switch off the first 2 materials because 25 and 26, if you remember, 25 and 26 are concrete. I just want to see instead the steel materials now. Okay, so I switch them off and I go to the end of the analysis. And you will see that more or less the maximum value is 0.015 as a deformation. Okay. Now, if I do the same, and then let's say, for example, I want to extract, I don't know, here at this fiber, I want to extract the wall course, model stage 2. I want to extract stress strain in the steel rebar. So strain here, vertical strain against stress and vertical stress. This one is rebar course. Okay, so this is what's happening now. It reaches values close to this one, of course, because this is the maximum value that I can get here. So it develops a certain amount of plasticity along the cycles. Now let's see what happens instead if I open the other model. So I impose the same displacement, but since the finite element are smaller, the deformation are more localized, and so the steel rebars are more activated. So I go on Implex here, which is the fine mesh. Now I need to increase it a little bit more to visualize the rebars. Now here at the end, some rebars are completely broken. They are at 60%. So of course I want to go a little bit here when the deformation are still, okay, still meaningful, okay? Then let me pick one of them more or less at the same location, like this one, maybe. I extract the data and I want to see what happens to the end of the analysis. Strain, vertical, stress, vertical. For some reason I have 2 rebars, so let me unselect them all. Oh, because I still have the selection from the previous plot. Okay, so let me create it again. In fiber color map, fiber strain, vertical, increase the size a little bit. Well, here already you can see that there is a much higher deformation. But let me go at some of these points. Okay. So there are many points where the deformation is much, much larger. Okay, so let's, for example, click something here. Okay. I want to get rid of them. Okay. So let's pick, for example, some of them. And extract data. Stage 2, not the model course, but the fine mesh. Strain, vertical, and stress vertical. I didn't pick the right value. Sorry, I picked the concrete, I think. Oh yeah, because I have to switch off the concrete fibers. Sorry. So unselect, let me pick them again. Okay, so this is a rebar here. I'm developing more deformation, but if I pick some other of them, I will see much more deformation also. You can see it clearly from here, okay? So as I keep on increasing, well, you have some of this value which actually should be broken, but if I clamp the values to, let's say, a maximum of and a minimum of minus 0.06 and 0.06, because I didn't input the maximum deformation. You can see that some of them are very close to this value, okay? So if I extract, for example, this one, probably before I picked some of one rebar that was not too much into plastic regime, but this one you will see much more deformation. So fiber strain, stress, vertical, rebar fine. Well, I picked two of them now. But as you can see now, the deformation is much larger. It's reaching values of 0.03. Okay, so this is the only reason why you can see with a very fine mesh, you will be able to have this major energy dissipation here due to the activation of rebars. When the mesh is very coarse instead, since the deformation is mirrored over a larger element, the deformation does not localize so much, and so the rebars, they do not go very deep into large deformation. But these are details actually, because in terms of capacity and strength, the model works very well also with a very coarse mesh and with reasonable times. Okay. So one last thing that I wanted to show you is for the automatic control of the IMPL-EX algorithm. Okay. Now in this case, I already used a very small time step because I need it for this kind of cyclic analysis. But let's do another quick test. Now I want to open the shear wall course IMPL-EX, so it will be much faster. Let me save it with a name because I don't want to mess it up. IMPL-EX country. And let me call it IMPL-EX control. Now let's imagine that here, instead of using, now I know what kind of time step to use for this IMPL-EX algorithm, okay? But let's imagine I start with a very coarse time step like this, and I'm using the IMPL-EX algorithm. I can see errors like, or errors, something like this. You see, the model will converge, but you will have some instabilities due to the IMPL-EX algorithm. Now, this is not so large as a time step, probably is fine, you see here. But if I decrease it even more, you see here some instabilities, which were not visible in the other model. You see here, stuff like that. So if you see something like this, you will probably realize that time step is too small. Actually, it took only 30 seconds to finish this analysis. But you can either reduce the time step to keep it under control, or if you don't know how to do it, you can simply create something which is called, where is it? Miscellaneous command, IMPL-EX automatic error control, activate. Okay, so basically this is a function where basically you can define the maximum allowed error in the range of 0 to 1. Well, of course, if you allow 1, it means you're allowing every kind of error. In my case, I would say, okay, let's allow a 10% error. Okay, if the error between the IMPL-EX algorithm and the implicit solution is less than the 10%, I will not reduce the time step. If the error is larger, I will try to reduce the time step to keep the error under control. Okay. Now, of course, if you do this, it may happen that you never reach that small value. So you have a limit on the reduction time step. So for example, in my case, I want to reduce the time step at most by, let's say, 100 times. Okay. Then you can choose the error type. You can say, okay, this 0.1 for me should be the maximum error in every Gauss point, or an average error over the entire model. This depends on the situation. Now, in my case, it is a very small specimen, and almost the entire specimen goes into deep nonlinear range. But if you're analyzing a very large building where only some portions are damaging, probably you would benefit from using the average, okay? Because using the maximum error may be too strict, okay? So now we'll just explain you how it works, just the basics, but I will do more webinars on this. But if you do this and you place it, of course, before the analysis, so let's put it at the very beginning. and I do the analysis now, you will see that at a certain point, the analysis will stop and will try to reduce the time step you see here to keep the error under control. Of course, it will take a little bit more than the standard implex algorithm, but if you are not very familiar with the implex algorithm, it will try to reduce the time step to avoid a huge error. So the advantage is that it will converge because it is implex, but you will be able to keep the error under control. The price will be that the duration of the analysis will be a little bit more, okay? And that's it, basically. Let me close OpenSees. I don't want to run the entire analysis. Okay, so I'm done with this webinar. Hope you enjoyed it, and we have, let's say, 30 minutes for questions. So if you have any question, please. We are here.
Hello, Massimo.
Hi, Linsun.
Hi. So thank you for your webinar. So I have several questions. So first of all, like last year, I spent a lot of time on the mechanic wall with damaged TC3D. I saw that you mentioned this material model has the one advantage, because if you push one side, it damage on that side. If you push another side, it will start from the initial condition. So that's partially why this material is can make it work. In your mind, is there any other stuff can make this material, better than damaged TC3D?
Yeah, there are many. I mean, the first one is that now you have more flexibility in defining the tensile and compressive behavior. Okay, so that one is an advantage for managing to model a broader cast of concrete. Okay, the other thing is that now you have two main changes that we did to the theory of the constitutive model to avoid the premature error, the premature failure we had with the damaged TC3D. Two of them. So one of them is the anisotropy of the crack of the internal variables that I told you. The other one is a little bit more difficult to explain. If I want, I can try to explain it to you, but let me see if I can explain it in simple words. But if I go to the theory here and you look at these equations, I made a small change. So here the negative surface, or actually let's start from the positive tensile surface is very similar to the negative one. Okay, it is defined as the a function of the principal stresses, sorry, the invariance of the stress tensor, but of the full stress tensor. And this tool here is used to deactivate the surface only when all the eigenvalues are negative. So just to explain it, if you are in the plane stress condition, so sigma 1, sigma 2, the tensile surface will be something like this. Okay, so it will be active in the positive size, in the positive negative and positive negative sides of here, because here you have positive and negative eigenvalues. Here it will not be active, so it's like the surface will expand infinitely in this direction. Okay, and this makes sense because you don't want the negative stresses to affect the tensile surface.
I see.
Now, previously, in the damaged TC3D model, I made the same concept. So I used the negative surface, which was like a Drager-Prager like this, which was not active only in tension. Okay. So what happens is basically when you were under shear, you were damaging both surfaces, and this makes sense. But the problem is that if you were in this quadrant, but very close to uniaxial tension like this, instead of damaging only tension, you were completely damaging also the compressive surface. So if you apply a stress like this, you were damaging also the compressive surface like this. That's why the old material model was damaging a lot. Now I made a instead of using this tool, I simply made this invariance function of the negative stress only. So basically it means that my surface will open like this now. So it will be active only here. So the global surface at the end of the day will always be like this here. There is no change in the global overall surface. But the point is that when you have stresses which are in the tension compression quadrant, but very close to the tension only, it will not damage the compressive surface. And this is a major improvement. And this, together with the plasticity, will give you this kind of behavior that then generates the pinching then I'm in the cyclic test. So if I do I already saved it in the Excel. No, I don't have the Excel anymore. So let's do a test in shear. And let's put some pre-compression. (1,000 division, 10 cycles is fine, but I need the symmetric linear increasing. And that pre-compression, where is it? 0.001 and minus here. Is it okay? Cyclic, symmetric here. Gamma. Oh, let me put it 0 here. Just a second. Okay. Oops, monotonic. Okay, so this is what happens here in this case. Then I put minus. Oh, but here I'm working in kilonewton. That's why I have to put it okay like this. So this one is the behavior when you don't have no pre-compression, and this is what you have when you have compression. Okay, this is fine. So the 2,000 kilonewton, the 2 megapascal that you have here of pre-compression is giving this residual plateau, and this is normal. But when you do in cyclic, so symmetric linear increasing, what you see is this one. So you develop plasticity here, then you go back on the residual compressive surface and you go back here. So this kind of sliding basically is giving the pinching behavior in the global response. Okay. So these are basically the two major differences.
Okay. I have another question. So basically, I noticed a very strange behavior. So when I use OpenSees MP in my for my damaged TC3D for the messianic wall, so when I use the partition is 4, and the result is this. When I change the partition, to 5, 6, or 8, sometimes if I do more partition, probably the analysis will get stuck or just failed. So I'm curious why, it's sensitive to the course I ask for the analysis.
No, I mean, it can be due to many things. What kind of constraint handler you were using?
I'm sorry. Can you say it again?
Yeah, what kind of constraint handler you were using? Because we found that when you have multi-point constraints and you use the transformation method or the we found some issues when you have many partitions. We still have to understand why. It is something inside the transformation method in OpenSees that sometimes it can give problems. So when we see problems like that, we switch to the penalty constraint handler. The reason is that the transformation handler is changing the number of equations. Okay, so it may happen for some reason, and I still have to debug them. Why? When you have the same constraint in some partition, you may have a different number of equations, and it doesn't match the equation on the other partition. So sometimes it may happen. So if you typical rule would be if you have multi-point constraints and you experience problems like that in OpenSees MP, just switch to constraint handler, to penalty constraint handler. Okay.
I see. Okay. One last question. So I noticed your computation time is very fast. around 20 minutes for the fine mesh. But for my model, like ASDConcrete3D, I use embedded approach. It took me 6 hours to finish this analysis. Do you have any idea why is your model is way faster than mine? Is because you are using smear approach or
exactly. Now I made it much faster. So I tried to put much more accuracy inside the three-dimensional constitutive models, so that you don't need to put all the embedded rebars and all this stuff. Okay. So in this model will work very fine also with a very coarse mesh and with these smeared rebars. Okay. Now, if you want more details, as you can see here, fine mesh is better, but already with a very coarse mesh, the results are very good. Okay. So something like this one. So the point is that the constitutive model now is much more stable, and with this kind of anisotropy, it introduces a lot of, it describes much better the material model in such a way that it is not so much important how you describe steel and all the other stuff. As you can see, I didn't pay attention also to how to model the top beam. I didn't model anything at the bottom. The boundary columns are just shells with a single mesh. It's not so important. So the constitutive model here is doing a lot.
Okay, thank you.
Welcome.
Yeah, thank you a lot.
Yeah, then we have Nicola Tarque and Professor Ponte, please. Nicola, go ahead.
Yes, thank you. Hello, Massimo. First of all, congratulations for the work done and for the seminar. I have understood many things regarding the model, and I see this. One of the important things is that the pinching effect can be reproduced. You know, I mean, some masonry test. When I mean masonry, also I talk about earthen materials. This is the problem, and then we will test this model for reproducing the cyclic behavior of the plane actions in the masonry walls. I don't have questions, just comments. A good idea could be also to test that model with material with low elasticity of modules, like Adobe earthen materials. When we are talking about 200 megapascals, and we found that, for example, in concrete damage plasticity that Abacus had, we had some problems. So it could be good also to test that this model with low elasticity of module materials. And again, congratulations and thank you very much. And just I'm surprised that here we have I have seen here in the panel also people from South America, especially from Peru and Chile. We are interested in using this model for reproducing the masonry behavior, confined masonry especially. Thank you.
If you want, Nicole, and if you have some examples that you know that didn't work well in Abacus, you can send me an email with the information about them, and we can say, for example, the next webinar could be on modeling Adobe, and we can try to do this topic on the next webinar. What about that, Nicola?
Sure, Massimo. Yes, we will keep in touch by email later.
Sure. If you send me all the details for the model, I can try to reproduce the micro model of Adobe. If you were pointing to micro model, I don't know, or macro model, and we can try to do that. Or we can compare model and macro model with the orthotropic raptor also. Let's say that the next the next webinar will be the application of this model to masonry-like materials. Okay.
Of course, already scheduled. Thank you.
Perfect. Please, Joel.
Yes, Massimo. Again, thank you very much for your excellent presentation, as always. I have two questions. One is your new model. Does it also capture the, in the unified compression field theory of Mike Collins and so on, University of Toronto, when you crack in one direction, right? When you crack in one direction, in the perpendicular direction, it weakens the compression strength of the concrete.
Actually, it is. Well, actually, it is taken into account in two different ways. One is because the compression field stuff and all that things, they were used in in non-tensorial models, so they didn't have the concept of the surface. So when basically you have a yield surface like this, you're already doing that. So for example, if I am in uniaxial compression, I have this strength. If I am in biaxial compression, it increases. If I am in compression tension, it decreases a lot. So there is already an interaction like that. The other one is what I told to Lin Sun before. So now basically when you switch on the orthoscopy of the internal variable, this is exactly what it is doing. So imagine that, imagine you have a sphere, okay? Now I will draw only a circle and I will draw only 90 degrees, okay? So imagine you have a crack at 0 degree, then another crack at 90 degree, and then you have some other cracks here. We typically use 4 subdivisions, okay? Now imagine you first load in this direction, so you are damaging either compression or tension. I apply the same concept on both tension and compression. You have a stress that goes in this direction, okay? So it damages along the history something like, let's say at this point. So this one will be a damage of 0.8, for example. Now in the other cracks, they do not experience any damage due to the direct stress that you have here. But actually, as I told before, we have this smoothing angle. So in the smoothing angle, basically what I'm doing is to smooth the damage that you have here around the neighboring cracks. And
I understand that.
So difficult to represent in 3D, but if I flatten this like from 0 to 90 degrees, and if I put it in a graph like this, so where I have damage here and the degrees here, I damage instantaneously this point to this value of damage. At these points, the stress was never gone in that direction. So instead of damaging only this one, I also apply a smoothing, which is basically a bell-shaped functions using 45 degrees or whatever you put there, okay? So yes, it is affecting somehow the what's going on in the other directions. Just to show you this, let's clear all the drawings. Just to show you this, for example, I can go in the concrete here. You see here, I activated the smoothing angles. Let me go back in shear. So cyclic, symmetric, linear increasing, 0.001. Then I put 10 cycles, 100 in shear, and then I put confinement, 3 megapascal. And 3 megapascal. Okay, and of course I have to watch this one. And what? No, sigma 1, 2. Yes, gamma 1, 2. I have to push it here, minus 3000, 3000. Oops, here I have to control the stresses. Perfect. Okay, so this is what I have now. If you remember, if I switch off the crack planes, you see, I will not reach the point here. Let me push it a little bit less. Okay. Oops. No, that was fine. Okay, so here I was loading up to 4.5 megapascal, then I go down, I have softening, I go here, and I have the same damage. So this one is an isotropic damage. If I switch on the crack variables, you will see that now I will restore the strength here. But if I increase the smoothing angle a lot, like let's say, let's go to 90, you will see this effect will diminish, okay? And if I increase it a lot, like let's say 1000 degrees, which means I do a complete smoothing, I should go back, you see, to the solution of the non-cracking plane. You see? So basically, the smoothing angle is how much the damage on a direction is affecting also the damage in the other directions, okay? So this one is a value that we tested, it works pretty well.
Yeah, but when, you know, because if you remember, the issue is with the shell element was very hard, right, before to capture, let's say, a behavior like the mestianic wall when you have a lot of shear flexure interaction and very large shear cracks, right? Because like you said, you have too fast accumulation of damage, but the beam truss model, right, that was the one that is claimed to be able to capture these phenomena very well. I think the main reason for the beam truss model, one of the main reasons is that they communicate the strain between truss elements that are perpendicular, right? So if you have a truss element that is in tension with cracks, it communicates to the truss element that is perpendicular to it to weaken the compressive strength of that element. And here you go back in the perpendicular direction, you go back to the full initial compressive strength, right? Or can you change that?
Two different things. Now I understood what you're saying. Those are two different things. So the fact that a truss model, let me do a drawing of the truss model. So if this was a quad representing by a truss model, and I have
now Massimo, it looks like from your presentation here that now you are able to capture what the beam truss model was able, but with a shell element, and probably even do better with these other phenomena that you capture. Sorry to interrupt you, but go ahead.
Yeah, no, it actually is pretty much the same thing. That's why there are two different things. So as you know, the truss is only aware of the strain in this direction. So they did a modification. So they created a truss with 4 nodes, okay, in such a way that they get the direct strain from this model, from this truss, and they take the orthogonal deformation. Now, due to the orthogonal deformation, they change, if the orthogonal deformation is tensile, they change the strength of this truss. So imagine that the strength of this truss starts from a certain FC, and this one, and here I have the orthogonal deformation, let's call it epsilon t, the strength decreases, okay? So this is actually what they do with the surface is exactly the same thing. So if I look at my surface, which has a shape like this, okay, in the plane stress condition, it is exactly the same thing. So here, where I am in sigma 1 equal to FC and sigma 2 equal to 0, and of course sigma 2 is related to the orthogonal deformation. Here I have this strength, which is equal to FC. But if I am here, the projection on FC is smaller. Okay, this is an FC reduced because I have the strain on the orthogonal direction. Actually, something that the truss model cannot capture is that they do not include the increase in compression under biaxial strain. They should do something like this, for example. If the transverse deformation is negative, I should increase it up to a certain value. So basically, the effect of the transverse deformation is taken into account by the yield surface. The problem is that since they didn't have a yield surface, because it was a truss model, they invented this stuff, okay? So that thing is taken into account already by the surface. Instead, the reason why we added the directionality of the internal variables was because actually this was something that we saw on the beam truss model. So the concept was the beam truss model is a collection of trusses like these, for example, for the vertical cracks, and then for the shear cracks. Now, this crack here, this strut here, it communicates with these points just to get the strain on the orthogonal direction, but it doesn't communicate with any other truss element. So basically, if I have a crack here due to the tensile opening in this direction, this one does not affect what's going on in shear. And so our anisotropic internal variable is trying to mimic this thing here. So the concept is that if I'm damaging in this direction, because I was shearing like this, I want, when I shear on the other direction, I want to have the same strength, because now this opening will close, and now we'll need to open a brand new crack to show softening on the other side. Okay, so there are two different aspects. Okay, I don't know if it is clear.
Yeah, no, I understand.
Yeah, there are two different things.
But let's see what you drew there, right? What you drew. Look at the crack that you did from the top left to the bottom right.
Yeah.
When you open these cracks in your model, what you're saying automatically, you will have a weakening of the FC prime or of the strut of concrete that are in that same direction as the crack, right?
Yes, but it's not like that actually. What I mean is that take a point here, okay? Like here, when you have compression and shear, okay? Instantaneously, here you have tensile deformation in this direction and compressive deformation in this direction.
Right.
Basically, when I analyze this one and I plug this stress tensor inside my yield surface, I will be somewhere here where I have a negative eigenvalue and a positive eigenvalue. So I will be here. Now, if I project this point here, it will be less than the pure FC.
Yeah, so it's already, like you said, it's captured by the yield surface. So the most, you think out of all the changes that you did, the one that able to capture the experimental result, cyclic result of the messianic wall, you think it was your smooth, your anisotropy, the smoothing of the anisotropy that you explained? Or?
No, it was due to two things. One was the anisotropy of the internal variables, but the other, the very important one, was the shape of the compressive surface, because before the compressive surface was active also in these points, okay, also here. Now the compressive surface now here is only affected by, it's only like this, for example, it's like a ranking on this side, in such a way that the tensile behavior is mainly dominated by the tensile surface unless the stress values are very high here in compression. Before,
I see.
And before, the problem was that the tensile surface was active up to this point, okay? So if you are in pure tension, the tensile surface was not active. But as soon as you move a little bit into tension compression, even if the compression was a very small portion, it was activating the entire surface. That's why it was reducing a lot the entire domain. So basically, what physically was happening is that a tensile crack was actually inducing crashing inside the material point. Okay, so that's why we decided to open the surface here, not to let the compressive surface be affected by tensile surfaces like this. Okay.
Yeah, thank you very much. I understand. And then the second question is, do you remember when last summer you presented the messianic wall, you were applying the boundary condition to impose the displacement at the top of the wall differently? You had something that would, I forgot now, it would reach different side of the wall. Now I've noticed you put a linear elastic beam, very stiff. You take the middle point, and from that point, right, you push left and right, right? And so your results are independent of this.
Because what was happening before, as I said, since the material model was damaging too fast before, then I had to pay a lot of attention to the boundary condition, but simply because the material was a lot unstable under those conditions, okay? Now the material is so stable that even if you put slightly different boundary condition there, it is not going to change a lot, okay?
Yeah, I understand. Yeah, thank you very much, Massimo. Unfortunately, I have to go. I apologize, but thank you very much.
Okay, thank you. You're welcome. We have...
See you in a couple of weeks.
Hi, Guido. I'll call you soon.
Yeah, absolutely.
Question from Chile.
Hey, Massimo, here from Chile. Very, very, very nice presentation. Omar is waving at the back there, but he's blurred out.
Yeah, but I imagine it was Omar.
And you know, no, just to congratulate you and everyone at ASDEA. This is such a huge contribution to OpenSees. You cannot even imagine. You probably imagine, but it's. I've been waiting for this for a very long time for this to get pushed. So it's huge, and I don't know. This is all great and very in-depth explanation that I really enjoyed. I wanted to ask you: do you have a sense of how much slower the integration gets when you go into plasticity? So let's say if in linear, when there's no damage, that is 1. What is the slowest time you expect for this constitutive model? Actually,
I didn't do the computation of the mega flops that you take for doing the computation, but it's not that much, because inside the constitutive model, I'm not iterating anything. I'm not doing any iterations. if you look at the computation, is not that much. Actually, you can look inside the code, but basically, the only computation that I do is the computation of the eigenvalues, which is the most expensive one, to compute the invariance. From there, I don't do anything special, because once I compute the invariance, I have the equivalent strain. The equivalent strain is a scalar. I plug it inside the damage tensor and compressive curves, and then I compute a couple of scalars. I don't do anything special. The only thing that may be a little bit costly is if you exaggerate with these values. But simply because, for example, once I compute the eigenvalues, I need to find what is the closest normal to activate the damage in that direction. Okay. So if you have 4 subdivision for 90 degrees, I have a unit sphere. Due to symmetry, I have twice that one, but it is in 3D. Okay. So for 4, I think it was 8 by 8. Okay. So if you increase that a lot, you can rapidly go to thousands of normals, and then you have at each iteration you have to find what is the closest normal. So my suggestion would be 4 normals are fine. If you want, you can put 8, but if you exaggerate here, the cost will grow a lot. Okay, so don't do that. But it's not even necessary, because taking a spacing of like 20 degrees between each crack is more than enough. Okay,
I was thinking about that, and I think 4 might be more than enough to resolve most of the stuff you want, I think. But yes, I was wondering exactly about how much extra cost is with the crack planes coming in. Now, regarding...
The only cost is basically finding what is the closest normal. And I simply do by comparing for example, the principal stress direction with all the normal cracks by taking the dot product, and the minimum dot product, the maximum dot product, sorry, will tell me what is the closest normal. Now think about it and repeating for thousands of planes in every,
of course,
it can take a little bit. So 4 by 4 is fine, because I think it was a total of 64, less than 64 planes, because there are the poles which are singular point. But yeah, let's say this one is a good number. Do not exaggerate with that.
Cool. So I'm not, one last question. I'm not used to this whole regularization thing that you do. I understand why it's needed and a little bit of how you do it. I was wondering whether something similar is needed for your rebars.
No,
Not really.
Not really. I mean, the regularization is only needed when you have softening. Okay. Now the point is that so the concept of fracture energy is that when you have softening, you cannot talk about strain, because a strain is a measure that makes sense when the displacement is smooth. Okay, in such a way that I can say, okay, instead of talking about the displacement, I talk about a normalized displacement, which can be the strain. Okay, but when the displacement is not smooth, talking about strain is not reasonable anymore. And the simple reason is that imagine that you have 2 different specimens, one like this and one like this. Now the thickness of the crack is independent of the size of the specimen. It depends, for example, in concrete, by the size of the aggregate. So the fracture process zone was something like 2.7 times the maximum aggregate size. Okay, because the crack has to pass through the aggregates. So let's say that the crack has a thickness of about 5 centimeters, 3, 4, 5 centimeters totally, like the total crack. Then the same thing should happen in a smaller specimen. Now the concept is that since the physical size of the crack is the same, if you take the total displacement here, which is 0, 0, and the entire displacement jump concentrated in this point, you will have the same displacement jump on a smaller element. But if you take the strain, you will divide the displacement jump by the total length here, and you will do the same here. But here the deformation will be much higher, simply because you divided the same displacement jump by a smaller length. Okay. So basically, this is the same pathological things that happens in finite elements. Okay, so if you have a smaller element, you will see a larger deformation. So you have to change the amount of fracture energy in such a way that the total dissipated energy does not depend on the size of the finite element. Now, there are other ways for doing them, which are the non-local continuum, but they are a mess to implement. It will be a mess to implement in OpenSees. And they actually require the finite element mesh to be smaller than the fracture size. I don't know if you heard about non-local continuum.
No, I've heard about that a little bit, just in
Yes.
theory. So I was thinking whether, no, it's going to depend, I guess, in the constitutive model that you're using for steel, because if you want to break bars and go all the way to
that case is fine. I mean, I said rebars because I didn't consider fracture.
Yeah, I've heard. Yeah.
The rebars, then you need it, also in the rebars. Well, the concept is that whenever you have softening, you have to consider that.
Yeah, with the softening.
Because when you have softening and strain, you are putting garbage there. So what you are putting there is referred to the size of the specimen you use to compute the strain. So if your finite element size has the same size of the specimen, it's fine. If it has a different size, it should be regularized. And that's why we need the fracture energy regularization here. So yes, if you plan to have steel and you want to model softening in steel, yes, you need it. You need to do it also in steel.
But that should be implemented in the specific model.
Should be implemented because actually now you gave me an idea, because actually the next step that I wanted to do in one of these webinars is to put the fracture in steel, but yes, then you don't have regularization. Now, many people do not consider it just for one reason, basically, because when you break the steel in a reinforced concrete structure, you're basically at the very end of the analysis. So
yes,
if you want to regularize it or not, is in some cases is not important, but in general, yes, you need it. So it should be done. But what I was thinking actually is it was to implement a material similar to this one, where basically the user can give stress and strain by points, and also the amount of deformation and damage. So basically it would be a 1D copy of this one. And it will be usable also for steel at that point.
that's very cool. Hey, thank you for all your stuff. It's amazing, and amazing visualization stuff, the cracks and everything. That's so cool.
Yeah, I made it exactly for that, because it was a mess to visualize the cracks with a very coarse mesh, and with the crack tool it was pretty fine.
We're going to start using this stuff right away. We were talking about it, so great. Thank you.
You're welcome.
Thank you, Jose. Night, everybody.
Okay, so if there are no other questions, by tomorrow we will put on the website the recordings and all the files that we did today. Okay, so thank you very much, and see you in the next webinar. Bye, everyone.